welcome to Thorlabs. My name is Matt, and today I'll be discussing how to use the Kinesis libraries in the C# programming language to perform a raster scan with the Thorlabs motion control stages. For this demonstration, I have here with me a Kinesis benchtop brushless motor controller and a 2-axis stage. Before we begin though, I would like to give a bit of background on what a raster scan is and a few different ways that this can be implemented. A raster scan is a rectangular pattern of movements that seeks to capture or reconstruct data over a two-dimensional area. This type of scan has applications in areas like computer science and display technology, but for this conversation we're going to focus on how this applies to image and data capture. Let's say, for example, that we have a laser incident on a sample, and we want to record some signal feedback from that illuminated point over a section of the sample area. Well, in a traditional unidirectional raster scan, this sample area is scanned starting from one corner and then moved horizontally to create a row. The vertical position is moved, and the horizontal position is reset so that the next row is scanned in the same direction. In this case, all data is scanned in this one direction. Similarly, the bidirectional scan starts in one corner and moves horizontally, but the horizontal position is not reset for each row. Instead, every second row scans in the opposite direction, which allows for data collection in both directions. Data collection during both scan types can also be done in a few different ways. Let's say, for example, you wanted a high-resolution scan. Well, in this case, you could take data continuously, while your laser or stage moves at a constant speed. This can be rather difficult to implement though, because the motion of the stage and the data sampling need to be precisely synchronized. In this case, any subsequent data reconstruction also needs to account for transition points where the stage resets its horizontal position or changes direction. An alternative to this is to use a step scan approach, where the laser or stage makes discrete movements and then pauses while data is being collected. This approach is a bit more easy to implement and less timing dependent because motion doesn't typically happen at the same time that data is collected. This approach also allows for acquisition dwell time to be added for each collected data point. And in the case of this demonstration, we'll be implementing a bidirectional step scan for our 2-axis stage here. And now let's move on to how this is programmed. On the screen here in front of me, I have a blank C# console application open in Visual Studio. I have this named Raster Scan Insight. I also have the Kinesis libraries referenced, and the project platform has been configured to work with the 64-bit Kinesis libraries. If you would like to see a more in-depth explanation of how this is done, please see our previous Kinesis software insight. For the program imports, I'm using the benchtop brushless motor CLI, the device manager CLI, and the generic motor CLI. I also have the system.threading namespace imported, and this is just going to make any kind of sleeps that we need to put into our code a bit easier to type. I'd also like to mention that a lot of the initialization code for the controller and channels is carried over from the previous insight, so I'll be moving through this quickly where possible. So let's start by building our device list. And this is going to be surrounded by a try catch that'll just handle any exception thrown by this method. Next, let's get our list of serial numbers. And this will be filtered to only return our benchtop brushless motor controller. And let's just use an if statement to make sure that this return serial number list is not empty. And if it does find a serial number, let's print that one to the console. And if nothing is found, the return will close the program. Next, let's initialize the controller chassis. We'll just call this controller. And if statement will be used to make sure that this is not returned null. And then the controller will be connected and the settings loaded. Channel initialization is also carried over from the previous Insight video, but this time we're going to be initializing two channels instead. These will be named x-axis and y-axis, and they're assigned using different integer inputs to the getChannel method. And just like with the controller, we're going to check that both of these variables are not null. And then continue with connecting the channels and loading their settings. Now we're going to start the polling loops and enable each of the channels. And just as a small reminder, we're going to be adding small waits in between each of these methods, and this is just going to give the controller a chance to update its internal status before we call any move methods. Next, let's create our move helper methods to encapsulate the MoveTo and home methods. The home stage is going to take the brushless motor channel as an input. The move stage is going to take the channel and an additional position as the input. Let's also create a third helper method that's going to encapsulate a new move type called the jog. And what the jog does is it moves the stage in a specified direction. And this method is going to take the brushless motor channel as an input as well as the motor direction. And this motor direction type is an enumeration taken from the generic motor CLI class. Now each of these move helpers are going to start the same way with a try-catch surrounding their move types. So just to make things a bit easier, I'm going to copy and paste these between the methods. In the home stage method, we're going to call home. In the move stage method, we're going to call the MoveTo method. And jog in the last method. Let's also add some console prints to the beginning of the home and move methods, and this will allow us to track the program flow later on. And we can also fill in the console prints for if one of these moves throws an error. Moving back up to the main body of the program, let's add a home for each of the channels. And now we can set the movement velocity parameters for each of the channels. Now the jog and MoveTo methods actually use two different velocity profiles. So if desired, you can have different velocities set for each move type. In our case here, we're just going to set these to be equal. So for the jog move type, we're calling set jog velocity params. And for MoveTo, we're going to be using the set velocity params method. Next, we're going to define some variables that correspond to some of the scan parameters. Starting with the start and stop positions for the X and Y scans. We're going to set X to be 25. And Y to be 50. Next, the stop positions for each of the axes. Here, X will be 75 and Y 25. And next, the number of points that will be scanned in each axis. And with these parameters defined, we can go ahead and set the distance that will be covered for each channel when the jog method is called. This is done with the set jog step size method. And here we're just going to set this equal to the absolute value of the end position minus the start position, and then divided by the number of points in that axis. And two additional variables will also be needed to store the directions in which each of the axes will travel. Now, both of these variables are initialized to be the forward direction, but this doesn't account for cases where the start position of one axis of the scan might be greater than the end position. And in this case, we would want the stage to move backwards instead of forwards. So to account for this, let's add an if statement that checks whether or not the end position is less than the start position. And if it is, we can switch the direction to backwards. Before the scan starts, we want to move each of the channels to their start position. To instruct the stages to move in the desired pattern, we're going to use a set of nested for loops. The first loop is going to use the variable I, and this is going to be used to control the y-axis. And the second loop, which is going to use the variable j, will be used for the x-axis. And we want each of these loops to iterate as many times as we have set number of rows or number of points in the x-axis. Now, because we already have the y-axis at its start position, we don't want it to jog on the first iteration of the loop. So to account for this, we're going to add an if statement that checks if we're in that first iteration of the loop, and if we are, we're not going to jog. And because we're skipping this first iteration, we also want to add 1 to the number of rows in the conditional of the first for loop. For each iteration of the x-axis loop, we want to jog the stage as well. Here is where we would add any kind of acquisition dwell time that would allow data to be collected once the stage finishes moving. To simulate this, we're just going to add a small wait. Just to show program flow, let's add a print to console to indicate that one of the rows finished scanning. And because this is a bidirectional scan, every time the x-axis finishes scanning a row, we want it to swap directions. Now to do this, we're just going to add an if statement that checks the direction of the x-axis, and if it's forward, it switches it to backward, and if it's backward, it switches it to forward. And before we could test our code, we need to disconnect all the channels in the controller. So let's start by stopping the polling loops and disabling the channels. And then we can call disconnect on the controller and add a small print to console to show that this has been done. Now let's run our code and monitor the scan. So we could see it found our device. The x-axis is homing. And it looks like there was an error thrown during the first homing sequence. So let's go ahead and close this. So let's go ahead and scroll down to the home method and see why this errored out. And looking at the wait timeouts set for each move, these were set to 6,000 instead of 60,000. And why this was a problem was with a wait timeout of 6 seconds, one axis wasn't able to finish homing before the next one started. So let's go ahead and change these and see if our code runs now. So our device is found again. The channels are enabled and the first axis is homing. Now the y-axis is homing. And now the stage moves to its initial starting positions and starts the scan. And the scan is complete. Hopefully this helps you in the lab someday. If you have any questions, please feel free to contact tech support.